So this is the high-speed display we are slowly finishing, and today I want to talk about this last digit. This increments with period 10 microseconds, which means that it changes the digit 100 times per second, 100,000 times per second actually. And there's quite a lot of interesting physics behind, and this is what this video will be about. This display will be used for calibration of high-speed cameras. We will explain the actual principle later. Because the display will be recorded as a video, it's necessary to render the digits clearly, so they should not overlap, they should not delay, and so there are several problems which can appear, and before we could accept this order from customer, we had to make sure that the last digit, especially the last digit, will be rendered correctly. So this was the question, whether Nixie tube can run so fast. So let's have a look at some possible problems. I will borrow one of the Zen clocks. First, let's have a look at how it should look. So these are waveforms. This is for, let's say, digit 8, digit 9. And this period on the last digit is 10 microseconds. So with a period of 10 microseconds, we are at frequency of 100 kilohertz. We want to see digit number 8 at the beginning of this period, and we want to disappear it at the end of the period, exactly at these places. So exactly when number 8 disappears, we want to start seeing number 9. So this is the optimum situation when there is no crossfading, no overlapping, no delays. The problem is that we don't actually know if Nixie tube can handle this frequency, because there were, or as far as I know, there was no application like this for Nixie tubes in the past. So we need to find out. So first have a look at the ideal situation. So let's imagine that this is the last digit, which is running at 100,000 kilohertz, and this is the optimal situation. You can see immediately after one digit disappears, another one is lit up. So this is the perfect situation. There is no delay between them, they are not overlapping, they are not crossfading, nothing like this. So this is perfect. This is the best possible situation where we want to be. Okay, now first possible problem. What if the digit doesn't start at the moment when we want, but a little bit later? So this would mean that we would have here a small delay when no digit is displayed. So it would be, the display would be flickering, and in case the camera exposure and shutter speed is set so that it can get into this exact moment, there will be no display, no digit recorded. So this is first possible problem, a slow start of the digit. You can see at the beginning of each digit there is a short gap, like a short delay, and if the camera takes the frame exactly at this position, there will be no digit display, or the digit would be very dim. Now another possible problem, what if the digit has some afterglow on it? What if it takes some time for it to turn off? So let's say it would look like this. So here we would have number 9 already visible, but the number 8 would be still a little bit visible here. So at this moment, at these two, or here at this place, we would see digit 8, and over it would be digit 9. What digit should be displayed in this frame, number 9 or number 8? This would be a question. So this is another potential problem what could happen. The turn of time is too long. You can see new digit appearing immediately, but the old digit, the previous digit, is still visible there. It's a little bit visible, and at the beginning of the frame both digits would be glowing roughly the same intensity, so it would not be visible, or it would not be apparent which one should be the correct one. And in extreme situation, let's say that the turn-off time is 30 microseconds, it would look like this. There would be 3 digits visible and it would be absolute mess. So this would be turn-off time 30 microseconds. So, do we want to lock it here? Carefully. Does it make sense? It's like, don't smile. Yeah. Don't smile. So we're just finishing the high-speed display. So today we are trying to explain how the Nixie tube works inside and all the things which happens on the background, so you can understand more. So we will split it into things. There are actually 2 things which happens inside the Nixie tube. One is the actual current flow from anode to cathode, or actually from cathode to anode. And another thing is the emission of light. These are 2 separate things. So we will first focus on what makes the Nixie tube conductive and how the current flow from one electrode to another. And then we will focus on the emission of the light from inside the tube.
We have here the model of our Nixie tube. Blue is the cathode, it's on 0 voltage, and on red, on the right side, we have the anode on, let's say, 130 volts.
So when you look on the Nixie tube, the anode is the grid, is the hexagonal grid in our tube, which you see around all the digits, around the stack of the digit. And the cathode can be any of the digits. If you see number 3 glowing, then this number 3 is connected as a cathode. So here we draw a symbol of power supply, so you can see that the plus is connected to the anode. This is always like this, and whenever any of the digits is connected to -4 of the power supply, then the cathode, then it behaves like a cathode.
So first we start with the atoms of neon, which are basically everywhere in the tube, and they can travel free around the tube. And now there are some electrons out there, and so the electrons are accelerated and they want all to go to the anode. So the electron gets more and more speed, and in this region, when the electron has enough speed, so this means the electron has some energy, it can hit an atom. And so the energy of this electron will cause that this atom is charged into an ion. This positive charge neons, they are accelerated by the cathode. So they are moving this way.
So what happens inside the Nixie tube is that we have, like, this is self-sustaining process. You can see that from every electron we have more electrons in the next step, and these 3 electrons are creating positively charged ions. So the electrons are turning these neutron atoms into ions, and they create more free electrons here. And at this state the Nixie tube is conductive, so we have enough of the ions which transfer the positive charge and enough electrons which transfer the negative charge. So this way, like so this is what makes the Nixie tube conductive. We have the the electrical current flowing from or through the Nixie tube.
Okay, so what does that mean for our display? So after switching off the cathode, it takes some time before the ions and electrons are recombined back, because they are attracting together and they will recombine back, making the gas inside neutral again and not conductive. But this takes some time, and we found out that this takes 1 millisecond. 1 millisecond is enough for us. We know that we don't need to go through ionization of the gas inside again. But the question is now, how are the ions and electrons distributed inside the tube? Because if they exist only in a narrow layer around the actively glowing cathode, it would mean that they either need to move from that cathode to the new cathode, or that the new cathode needs to create its own cloud of new electrons and new ions, and this may take some time, and during this time the glow might not be present at all, or the glow may be just very dim.
This is a core, 10 protons, and then we have like one internal shell with 2 electrons, and then we have one external shell. This is the valence layer with another 8 electrons. Now we have here a free electron which is accelerated by the electrical field from the anode. Like it travels this way and hits the electron in the internal shell. It will transfer its kinetic energy to this electron, and it will move it here to the valence layer. So now we have the electron in the valence shell. It's on the place where it doesn't belong, and it wants to return back to its original position, which is here. And it will happen, but it won't happen immediately. It takes some time, some very short time. And when it finally returns back here to this position, because this is a layer with higher energy, so there is some energy difference. This energy difference is the same amount of energy which was removed from the kinetic energy of the first impacting electron. And when it finally returns to the original position, it will release a photon, and we will see it as the orange light. Actually, this frequency of the photon is corresponding to this energy level. So this is some specific frequency of the photon. This excited atom, that it can exist for some short period of time, and it doesn't release the light immediately. This is important for us. So what happens if we switch off this? How long it will take for the glow to disappear? Now, how long it will take for the glow to disappear?
Yeah, and we don't know what's the half-life of excited neon atoms.
I'm sure that we could find it, but
maybe you will write it us in the comments.
Yeah, that's true. Yeah.
To make some after calculation if our tube behaves like the
Theoretical tube.
If we switch off this digit, there is no production of excited atoms and ions anymore. So we have some certain amount of excited atoms and ions around this digit, and they are traveling around, but we don't know how long it will take to disappear. Like they have excited atoms, and after a certain time there are practically no excited atoms around this digit anymore, so we cannot see this glowing.
And the presence of the excited atoms means that there is still light being produced on this cathode. So this cloud of excited neon atoms is producing the visible light. So even after turning off this cathode, for some short period of time, these excited atoms will still produce the light, but there will be no new atoms produced.
If we draw a chart like this is the number of excited atoms around this digit. Here we have the time. We have a certain level of excited atoms in the glowing area around this number 8, and after a certain time there is just the half excited atoms out there, and after the same time it's just a quarter. So the graph will look like this. It goes to practically 0, but we don't know which time.
Okay, again, so what does that mean for us? So when we turn off the active cathode, there is still a cloud of excited atoms surrounding this cathode, and these excited atoms will release the energy as a light in some short period of time. So after turning off the cathode, there are still some old excited atoms. There is still some visible light produced by the excited atoms, and now for us it's important to know how long are these excited atoms existing and how long will be this light produced from the old cathode, because if there is the old cathode still glowing and already the new cathode glowing, we would run into the problems what I described at the beginning of the video. There would be two digits overlapping. So let's hope that this is not too long. We again did some calculations with Sebastian, but this time we were completely unsure and we decided to explore this thing more practically than theoretically.
Okay, so it's clear that it's not completely clear, so for this reason we decided to make an empirical approach. We searched for a place where we could run the display and take a shooting by a really high-speed camera, and we found a company in Prague, and the owner of the company, which represent a brand Photon. Photon are really good high-speed cameras on the market. So they have a Photon camera and they offered us to make a shooting of our display with their equipment, so we could really see what's happening inside. But for the camera test we needed a device which would allow us to run our Nixie tube at 100 kHz, and at this time we didn't have any because we still didn't work on the electronics for this display. But what we had was a prototype of a blub clock. Blub clock is our new clock. It's a single tube clock displaying time just on one Nixie tube. And we decided to use a prototype of this clock for this purpose. So Sebastian wrote a short code. It was a simple application which was cycling through all the digits 0 to 9 in precise intervals of 10 microseconds. We decided to use assembler for this purpose because we wanted to achieve a perfect accuracy of the intervals, and this is exactly what assembler is good for. It allows us to count all the individual instructions and achieve best possible accuracy. Okay, here we are testing the display on oscilloscope. We had to achieve precise intervals of 10 microseconds, and the inaccuracy must have been in a region of nanoseconds. By the way, on this project we spent really a lot of time programming, and I still remember when Sebastian came. The first week he mentioned that he is really not a programmer, that he can do electronics and he can do it well, but he's not a programmer. And already in this project he worked so long time in programming of like a Python scripts and all the stuff for Arduino, assembler.
and later in the particle photon for precision timing and fast reading of the analog values on the input, we had to go under the level of the framework, of the wiring framework, what is used as a programming language, similar way like Arduino. Okay, so once this little display was finally programmed and tested, we could finally set out on the road to Prague. All the specialized services are usually located around the capital city, so they can be found in Prague, which is the capital of Czech Republic. And because our little castle laboratory is based in a small town Březolupy, which is on the other side of the country, we always need to travel for 3 hours to get to Prague. But in this case the distance really didn't matter, because we were so much excited to try shooting of our Nixie tube on a high-speed camera, because Tomáš Zahrádka, owner of the Proxys company, offered us using a Fastcam Mini AX, which is a high-speed camera capable of shooting up to 900,000 frames per second, so 900, almost million frames per second. So with this frame rate we will be 100% able to analyze what's happening inside a Nixie tube. Let's get directly to what we recorded. We ended up using a frame rate of 200,000 frames per second, which was a good compromise between quality or resolution of the picture and frame rate, because going higher would mean shrinking the resolution and going lower would mean not being fast enough for the analysis of the Nixie tube, because our Nixie tube is running at 100 kHz, so with 200,000 frames per second we are getting 2 frames per every change of the digit.
And we can use a step mode.
And this is finally the result, Nixie tube running at 100 kHz. So the answer is yes, Nixie tube can run that fast. There is a long afterglow on practically every digit, so the digits are overlapping, but it's very clearly visible which one is active, because the activation time is very short and the brightness on active digit is much higher than on the rest, so it's very easy to distinguish which one is active. So with just this video we were able to accept the order from customer, but we were interested in few more things. So first of them was how long exactly takes the afterglow. We set up the Nixie tube to number 8 and then turned it off and measured how long does it take for the afterglow to completely disappear. And as you can see here, going frame by frame, we can see the afterglow after number 8 for 40 frames. So this means that we can still see the afterglow for 200 microseconds. Fortunately, the brightness drops rapidly. Already in the second frame after turning off the digit, we can see brightness drop maybe more than 50%. So this makes very easy for us to say the exact moment when the digit was turned off. So as we could see, the startup time for already running Nixie tube is very short. The digit change is practically immediate. This means that the ions and free electrons are probably filling all the tube and there is no movement of particles necessary for the illuminating of the digit. But how is it with a cold Nixie tube? So we set up another test. We let the Nixie tube cool down for a minute or so to make sure that all the charged particles are fully recombined, and then we turn on number 8. At this moment, all the new ions needs to be created, so it takes some time and we were interested how long is this time. So again we went frame by frame and we counted 15 frames, which is 75 microseconds. This is significantly longer time than for already operating Nixie tube, which is under 5 microseconds. And just to remind, for our Nixie tube display, the window for a digit change is just 10 microseconds. I find especially this very exciting when you take a startup time of a digit in already running Nixie tube and compare it to startup time of a digit in a cold Nixie tube. It's such a huge difference. The running and ionized Nixie tube strikes the digit so fast. When you look on the left side, there is the already operating Nixie tube, and it can fully light up new digit 8 times before the cold Nixie tube light up only one number. Okay, so this video is getting a little bit longer, so just few last words on the end. This project might seem like very distant from what we normally do because we manufacture clocks from our Nixie tubes, but it's actually very helpful for development of our Nixie tube technology, because this is exactly the type of the project which forces you to go back to the drawing board and study how things works, and this is the kind of things which moves you forward and helps you get better understanding of the principle of the operation of Nixie tube. So thank you very much for watching, and definitely stick around if you want to see more from our crazy Nixie tube resurrection endeavor. Thank you!